So I shall give a relatively slowly paced talk. Let's write up over here, perhaps just to be chewing over a very simple case of what Umberto Zannier and I have proved is the following. There is a simple abelian fourfold defined over the rationals, not isogenous to a Jacobian, to any. And I promised in the abstract I would define all the terms, even though these terms have been used many times. Let's give some definitions, and this helps with the proof, the sketch of the proof at the end. So, abelian variety, of course. A, for me, is just the quotient of c to the g by some lattice. Say z 2g. So a discrete subgroup in C to the G of the maximum possible rank. Well, this is, we need to know a bit more about this. For G equals 1, this is okay. G equals 1, then this is complete, the definition. For G bigger than 1, then there are the Riemann relations, various conditions on these periods. If you just take any lattice here, then this will not give you an abelian variety. It gives you just a complex torus. Riemann relations. And I write some of these down. Let's put these column vectors into a matrix M. So that's G by 2G complex matrix. And then the Riemann relations are right in this form. So they should exist an integral, non-singular, alternating 2G by 2G matrix E with, and so here they come, M e to the minus 1, M transpose is 0. So this relation is pretty stringent. You have a 0 there. Well, this doesn't look like 0. The second relation is not so stringent, but says something. So here we have the complex conjugate. D is transposition, of course, is positive in the sense of omission. So this is a lot of inequalities, and this is, of course, the equality. This is automatic for G equals 1. there's always such an E, and you can take it as the simplest possible kind of alternating matrix, but for G bigger than 1 it gives you genuine condition. So that's defined abelian. Fourfold means, of course, G equals 4. I said I would define almost everything, so I've got some way to go. Defined over Q, I'm not going to define, but it's definable. Isogenous. So isogenous should be defined because there have been some talks here involving polarized isogenies, and I don't want to restrict to polarized isogenies. So that makes the definition simpler. I should be storing some things like here. So an isogeny from one abelian variety to another one, so with a different period lattice but the same dimension, of course, is or can be identified with an invertible C-linear map alpha, which of course descends to a map in here, and therefore you need alpha respecting the lattices. And that I want to store. So that's isogenous. Simple. I forgot simple. So simple, A is simple. If it is not isogenous to any A1 cross A2, CG1 not isogenous to any product, and the G's are always bigger than 1. So G1 so that's simple. And then Jacobian is the only thing that remains. So Jacobian abelian variety comes from, so in dimension G, comes from a smooth curve of genus G. So for example, G equals 1, I separated G equals 1 from G bigger than 1 up there. G equals 1, you would get a simple, you would get a one representation of an elliptic curve. And the lattice there, to see that it's really a lattice is involved, you look at the various integrals around a closed curve, and as you choose a closed curve and vary the closed curve, L, then you get a lattice. These generate a lattice. In C now, as L, there it is. G equals 2, for example, y squared x to the fifth minus 1. Then to get a lattice in c squared, one has to take two of these things. So holomorphic differentials in all cases. We're writing them as columns, so it would be this. And you have to be careful to integrate over the same curve, and these generate a lattice in c squared, and so on. So the Riemann relations, here we don't need them. The Riemann relations in general are automatically satisfied. And with slight strengthening, that we can always take the determinant of E equals 1. And if the determinant of E equals 1, then essentially we can take E as the standard, the simplest possible. So we can take E as, for example, so the signs and everything I always get mixed up with, but I've given this lecture before, so I won't get mixed up this time. E as 0 identity minus identity. And that makes these a bit simpler. Now, R becomes, if you write M is M1, M2, so split it into two halves there, that T is M1 inverse M2. The two conditions come down now to two conditions just on T, and T is symmetric with, so the symmetry condition, these are equalities, so these come from this one, and then the inequalities tell you that the imaginary part is positive definite. So we could normalize M to just multiply on the left, changing the basis of C to the G, and this would give you I T. And when this happens, then we have the situation of principally polarized. That's the definition. PP. So historically, of course, the Jacobians, so that's now I've defined this, the Jacobians turned up first, and then a kind of generalization was abelian varieties, and they are a generalization, although this is not clear for small values of G. For G equals, so it doesn't work simultaneously. Someone said it doesn't work simultaneously. So for G equals 1, 2, 3, two concepts of abelian variety and Jacobian variety are more or less equivalent. It's not quite true, but I think the precise truth is slightly complicated to explain, but it's not relevant to this talk. And I just say that certainly every simple abelian variety is a Jacobian. Every simple principally polarized abelian variety is a Jacobian. So for g equals 4, there is a discrepancy, a serious discrepancy. This no longer holds. And the best illustration of this is by counting dimensions. How many of these things, what's the dimension of the set of these things in some sense? And we can do this from the t here. If g is 4, then t looks like this. And these are already determined by this, and so that's 10. The dimension of principally polarized is 10. But the dimension of Jacobians, or this, what comes to the same thing, the set of smooth curves of genus 4, this is 9. I don't know a similar primitive way of seeing 9. I don't know if anyone can help me after. It's nothing to do with Gareth Jones's 9, as far as I know. So this is less than 10, so if you pick an abelian variety at random, you won't be in here. And so here one would have dimension 10, and the locus of Jacobians looks like 9, like that, if I, for the purposes of two-dimensional blackboard. And something goes funny down here, oops, and something goes funny down there, and the locus of the Jacobians is not closed in the set of abelian varieties. And I think these correspond here to Jacobians of stable curves, and I have to yet learn what a stable curve is. Curve with only double singularities, I think. But these difficulties here will disappear soon. So what would you expect from this? So expectation. Well, first of all, there is a principally polarized abelian variety of g equals 4, which is not a Jacobian. That's easy, there's one. And B, almost all. I could say abelian fourfold here. And one can make these very precise. The sets, I'm just talking vaguely about sets and draw them as things, but of course they're algebraic varieties. I have dimensions. These are the really genuine dimensions in the algebraic sense. And so one can get, for example, an abelian variety here defined over Q bar. So there is one. So we're getting close to this statement now, but we don't have this isogeny business. And this was introduced by Chai and Oort in 2012. Go further up here. Is there, well, a question to which this is an answer, yes. Is there an abelian variety not isogenous to any Jacobian? Here I can forget about principally polarized because isogenies come in and they don't respect principally polarized. Mine don't anyway. So here's an answer here, but this is still in the course of writing up, so this will be 18, I suppose. This question was immediately answered by Tsimerman. Actually, they asked a slightly stronger question, not isogenous to any Jacobian, so not isogenous to anything in here, say in this dimension 4, genus 4 business, also not isogenous to anything up here as well. So you even have to exclude this from the question. So Tsimerman. Both in annals, yes. And for each G at least 4. I think they attribute this question to Katz, and in a footnote then they say that Katz denies responsibility and says it's due to Oort. So they toss the thing around. I don't know who asked this question. Don't know really why anybody asked this question. But the introduction of isogenies, so you don't even allow isogenies connecting the things. So you want something not isogenous to anything in here. And as soon as you introduce isogenies, they're generally infinitely many isogenies. One can see this from here. This was a statement about lattices, then I converted the lattice into a matrix, and so if you put this, reinterpret this in terms of matrices, then you get alpha. So now I do get it wrong if I don't write it down. Alpha IT. I've been writing, all my notes are with round brackets, but I've started somehow square brackets. And then the corresponding matrix there for the second abelian variety. And then I'm not going to be able to keep this up with square brackets. Let me try. I'm going to go into round brackets pretty soon. So write it like this. You get a matrix here, and PQIs, these are integral. And for example, the determinant is then simply the index of this in this. So the square brackets here clash with these square brackets, never mind. And this is defined to be the degree of the isogeny. And you can have lots of things here. You can have infinitely many choices for this, although it's countable. And so if you start applying these isogenies, if you apply an isogeny to something in here, for example, you may go outside the box because it may not give you something principally polarized, but very often it will. I suppose relatively often it will, and if you apply it to everything in here, you get something like that. And then there's infinitely many of these things countable, and so I've lost that point there. And the defined over Q bar. It was in here, and it was in here, but it was not in here. And this is the problem, of course, that the sets here are then again countable, and if you are unlucky, you kill them all.
Didn't they also require simple?
Sorry?
Didn't they also require simple?
No. If it's not simple, in low genus, it's automatically in this bit. I just learnt this yesterday from Yuri Zahin. In small genus, in genus, well, to say this genus 4 business. So every product is actually in here. I think their examples are simple that they give. So I forgot to say also that here Chai Oort also answered yes. So the history is slightly complicated, went very fast, but yes, modulo Andre Oort. Tsimerman then asked, gave an unconditional answer of yes, and then slightly later proved this result here. So what are we doing there? Well, all these proofs, including all these proofs here, they were exceedingly ingenious, especially Tsimerman's constructions, and all the abelian varieties that turned up produced an abelian variety which is CM. And even Weil, what they call Weil CM, which means that the Galois closure of the CM field is as big as it possibly can be. So this answers the question. They produce a sequence of these things, and then sufficiently far off in the sequence, you can always find something that's not on any of these. So that was okay, but this is not really quite answered almost all, because as was already mentioned in the talk yesterday, the CM things are relatively sparse, and I think the example yesterday was the CM elliptic curves over Q. The CM elliptic curves over Q, there's only 9 of them. This is also nothing to do with this 9. So we thought it would be of interest to try and get almost all. I don't think this has any chance of producing almost all. And furthermore, the CM orders, these go to infinity in some sense, and so the degree of definition of the abelian varieties is probably also going to infinity. So if you want to stay over Q, then none of these proofs will work. There are other things involved in Tsimerman's proof, equidistribution theorem of cats, which Katz also denies, says it's someone else, and then rather complicated procedures to avoid Siegel zeros, and I haven't worked through the proof in detail. It looks formidable. So this is a simple case of what we've done. We've certainly got rid of the CM. So we produce abelian varieties A with endomorphism ring Z. So that's certainly nothing to do. That's the opposite of CM. And for a typical abelian variety, this will be the case if you choose it at random, like this. And then the techniques of the proof require one to actually to load this even more, and even A, which are Galois generic. So this I think implies Hodge generic, which certainly implies this, and defined over a number field, defined over fields of degree at most, I think 2 to the 16 G to the 4 over Q. And many. So I won't. So there's various formal theorems which I don't really want to state. So where's this? Lots of time. So the title was Avoiding Jacobians. That was sort of picked from Mumford's book on abelian varieties, where he says he wants to avoid the crutch of Jacobians. He wanted to develop the theory of abelian varieties without using Jacobians. But I'm now going to not only avoid them, but completely forget them. And this is the strategy also here, that one simply takes any old hypersurface in 9-dimensional thing, and makes it closed. So you forget about those things. And then the game is to try and, the question is then to try and find abelian variety defined over Q bar, not isogenous to anything in this hypersurface. So this will be A, the set of principally polarized abelian fourfolds, and this will be here B, an arbitrary algebraic hypersurface. And a consequence, since we've forgotten about the Jacobians, this remark is completely irrelevant now, and so the theorems apply to 2 and 3, provided you choose an interesting hypersurface. So, for example, for genus 3, we could show that almost all principally, so no, I don't need this, abelian threefolds are not isogenous to a Jacobian of a hyperelliptic curve. A curve of genus 3 is either hyperelliptic or it's not hyperelliptic. This is someone's theorem. And the hyperelliptic ones are the exceptions, so they look like this. Now it's dimension 6 and 5, and so you can rule those out if you want to, and even through isogenous. And there are similar, slightly less natural things for genus 2. For genus 1, it looks like you have no space, in the words of a previous speaker. But then you can, instead of doing things over C, you can do things over R2, and suddenly you've got some space. You've got 2 dimensions there, and so you can interpret this as in terms of a real algebraic curve lying in C, and then there's similar statements. So, to 20, does it start 25? 20 minutes left, I think. Yeah, okay. I have to talk more slowly now. Does it go up and down at the same time? No, it doesn't. So I start off again with this picture up there, A and hypersurface B. And we want to produce lots of things in here, which are not isogenous to anything in here, so one can think of those lines, but they just get in the way of the picture. And over here I went from abelian varieties somehow to matrices, and you can go back in the other way through for things like modular functions. And so in the map in the other direction, I'll just denote by J, as if it was just a one-dimensional modular function. And then the set of T's I'll write like this. So I write it like this because of the usual so it's one of those things. So it has sort of corners. And this is the set, this I'll call Roman or boldface T, which is a set of T's. And so you have a J going in this direction. And in particular, you have a pullback of this. So, and the pullback of this will look something like this, and then perhaps another bit there. So this here and this here are J minus 1 of B. So, right, various steps down. First step is to just produce a lot of abelian varieties in here, and hope you're lucky. Construct many abelian. So we fix D, an integer, and we construct many PPAV such that A is not isogenous to any Jacobian. So I have to write it a bit more carefully. Let me stick to G equals 4 and then over Q. Not isogenous to any Jacobian. If I stop there, that would be the proof. But the D comes in. That means through an isogeny of degree at most D. So as soon as you bound the degree of the isogeny, you've more or less, not quite, you've more or less cut down on the number of lines there. So you only have to avoid a certain bounded number of lines. And so this can be done by counting. The counting, so you want to count simple ones, and then you actually want to count, in the thing here, you want to count Galois generic ones, which is slightly more technical. And then you want to say that you've got many of them. But this can be done by counting methods. So pick any A from this set, from these. And then if that happens to work, you're done. If A fits the bill, okay, else there is B in B. So we're picking then an A at random in here, and if it doesn't work, then there's something in here and an isogeny connecting them. And I want to do it in the right way. Alpha with some degree D. And then, of course, this can't be in here because we would excluded those. So, I could write it in here. But I don't want to write to fill this ball up with too many lines. And then isogeny estimates. Enable us to assume that okay, so I go up here. This is not too big, it's bigger than D, of course. And so I don't want to write down, there's parameters in here going around, and all those parameters, I want to keep as many as possible out of the way. What will this degree depend on? The A's are somehow constructed and given, so these are sort of constants. They're not quite, but one can, for the purpose of this talk, I'll regard these as constants. B we know nothing about except that it lies on here. We don't know anything about the height of B, but as we've seen in a couple of talks, the height of B is more or less determined, and or at least an upper bound for it, is determined in terms of a height of this thing, which I'm saying is constant, together with this degree, and this degree comes in logarithmically, so that is harmless. What is not harmless is the okay, then you have the fields of definition of the abelian varieties. So this is harmless, this is over Q. This we don't know. We don't know what that is, and so I'll just put in dB to some power kappa, where dB is degree of field of definition of B. And kappa, I'm staying down to genus 4, so kappa is absolute. That's definitely absolute. These aren't absolute, these depend on parameters that you use here, but I will omit them. So how do we control this? And now it's this well-known strategy. We have alpha here, and we just take conjugates of B. If the degree is bad here, if D of B is bad, then it has lots of conjugate varieties. So you'll have B sigma, sigma in gal, and you'll get many of these conjugates. And if you assume that B is defined over the rationals, for example, then it'll all lie on that. Now B was fixed, so it's defined over some fixed number field, and if you just take a positive proportion of these, then the various conjugates will, want to get rid of this, will lie like this. These are the various B sigmas. And the isogeny will also conjugate, and you'll get various isogenies here. Alpha, what was it? Tilde, sigma, and the B sigmas here. So you get alpha A to B sigma. A doesn't get conjugated because it's defined over Q. So you have lots of these things. And now here, let's go now over to the Siegel space, and that means coming back here. So I already came back here with B. This is J to the minus 1B. And so I get a lot of so I get a T coming from A, as in this notation here, and each B sigma gives you something which lies on here, and I call that U sigma. The exponential here, the superscript here means real conjugation, proper genuine conjugation. I can't conjugate these things because they're not algebraic, so I put in a subscript just to indicate that they're. And then the connecting thing will be in here, and here is the connecting thing. Here is the relation between T and now this is U sigma. I'm using alpha in two different senses. This was the isogeny, and this is a complex matrix. This is bad, so let's immediately eliminate this confusion by eliminating T from this. If you're eliminating alpha from this, if you eliminate alpha from this, you get the well-known equation connecting just the T and the U sigma, and it involves some P's, and these will depend on, we certainly can't conjugate these because they're integers, so this will have to be a subscript, and we get a relation then relation U sigma equals these minus signs here were put in so they don't come in here. So that gives you the relation connecting the two Siegel matrices. And then this U sigma was in J to the minus 1 B, so this, of course, is in J to the minus 1 B. And now if you just look at this, this is a certain equation for P, Q, R, and S, and it's an analytic equation because of this is analytic and not algebraic. This part is algebraic, but this is not. And all this part is algebraic, but and so this says that P sigma, R, Q sigma, and this is, again, I don't have to be spelled too much out here for the experts. This is integral point on analytic variety. So some kind of Peeler-Wilkie will give you the number of P sigma, R, Q sigma, R sigma. S sigma is bounded by x to the epsilon. So here I have to go very fast because I've only got 1 minute. This is some kind of uniform version, and you have to take into account the algebraic part, which is maybe not empty, where x is an upper bound for the norms of these things. So we want to know how big large these matrices are. This question was addressed in the previous talk when the isogenies were polarized isogenies, and then you can get such things. But without this condition, you have to, instead of using instead of using isogeny estimates, if you use endomorphism estimates slightly later, then you can assume that these things are bounded. Essentially, the endomorphism estimates had as their aim describing all isogenies, not just the smallest isogeny, and they tell you that these can be then and we can assume x is also the same kind of bound that we got from the degree of the isogeny from the this. So the degree just gives you the determinant, and of course, if you know the determinant, you can't get at the actual entries. So here you can get at the entries if you use this sharpened form, and then you okay, that's it. And then you play off this against the degree, and you choose your epsilon so small that it kills the kappa, and then everything follows from what I've written on the board, but I don't have time to say it. Thank you.
Okay, so does anyone have any questions?
So what is the fact that the...
Chris,
I suspect this is a bit naive, but where did the fact that B is a hypersurface...
that comes in when you want to get rid of the algebraic part.
I see, okay.
Yeah, it is used, yes.
Yeah.
Further questions? So maybe one question from myself. What happens if you have an algebraic part in the pre-image of B?
Well, in fact, you can show that this does not lie in the algebraic part. I don't know if the algebraic part is empty or not, but you can show that this can't lie in the algebraic part, and that uses Ax-Lindemann for abelian varieties. Plus playing off, that brings in weakly special things. But if you load the hypothesis there, Galois generic, then this is not compatible with weakly special. It's the opposite of weakly special, so that you exclude. That's why this extra thing goes in.
Okay, if there are no other questions, let's thank David again.